Yeah.
So we will usually publish it in our YouTube channel. So welcome again to another episode. I think Kevin, unfortunately, he's on a plane today, so he's not going to join us as a usual co-host. So we're very glad to have Liam from Tao and Watson Chain join us today for the first time. So welcome, Liam, here.
Thanks. Nice to be here.
Yeah, usually what we do is we go through some things we released this week, and then if you have questions about it or anything about not about the released new features, we can talk about it. It's pretty freestyles, but I just want to go through the agenda first. So usually I just I don't know how often you follow our technical blogs, but this week we released something I think kind of interesting. A lot of people find it interesting. It's basically called we call it a partial preimage technique. So if you are familiar with hashing a Bitcoin, I think anybody who has been playing with Bitcoin for even just a while, you probably heard about hashing. So we use a lot of hashing algorithm in Bitcoin, like SHA-1, SHA-256, RapMD 160, and a bunch of others. So with this technique, is a very neat trick. Basically, you have to use this trick, you have to understand the internals of how this algorithm works. Because usually we try to treat this hashing algorithm as a black box, right? So you have inputs, you have outputs. Your inputs can be arbitrary length, like a random bits, any can be pretty much anything. And then you give you a fixed length output. For example, SHA-256, right? You can fit any arbitrary length data, and then it will give you the 256 output. So you use it widely. You can use it to derive Bitcoin address. You can use it to derive transaction ID. You can do it in SPV, Merkle tree. So a lot of times you come across SHA-256. So in this article, basically we instead of treating it as a black box, we treat it as a white box. We go to the internals of how SHA-256 works, because we're going to leverage this inner workings to derive some very interesting smart contracts in our case. So before I dive into detail, any questions so far, Liam?
No.
Okay.
Good. I'm familiar with that. We use it for mining as well, of course.
Yes, of course. That's an elephant in the room. So if you dive into the internals, so how it works is the algorithm actually works in I think 2 steps. First, you have the arbitrary length data, right? So usually we call it preimage. So you have to divide it into fixed length chunks. In this case, 512 bits. So what if you are not a multiple of 512? You pad it at the very end. That's what we show here in step 1. So for example, here you have 4 chunks. Each chunk is fixed length, 512 bits. And then you go through this like an iteration. Every iteration, it does the same thing. So basically, it takes this function, and it takes 2 inputs, the current hash. Basically, you have an internal state. I just call it H. It's kind of like you will see why we call it the internal hash, and also the current chunk. So you go through this, you have 2 inputs and give you another hash, the current hash, H1. So you keep going through this process. So now you have H1, and then you have chunk 1, then you go through the same function, it give you H2, same here, you keep repeating this process until you reach the last chunk. So you have no further new data. So then whatever the internal state is, this is just output as the final hash. So you may have the question here, what is the initial value then? Usually called the initial vector in like cryptography. So because this thing, you want to make sure it's truly random, right? You don't want to have some kind of a backdoor existing pattern. So, attacker may leverage this. So this use some kind of existing, I think, like a nothing up the sleeve kind of technique, you have to use this kind of from some existing entropy, that's not tampered with. For example, you may use it as the digits of pi, right? Or use it as square root of, I think in this case, they just.
Okay. Yeah, you just froze.
Yeah, okay, I was in the middle. Okay, thanks for waiting. Yeah, I'm talking about how do you get H0 part, right?
Yeah.
We still, okay. So basically you take some like entropy from some existing source, which nobody can control. For example, the digits of pi or the square root of, let's say, prime numbers, you put in there. So eventually you can get this is the hash 256 we usually see as the black box. So the G, because it takes, two inputs. One is, I think, 256 bits, and the other input is 512, and then output 256. So it's we call it in cryptography, we call it such a function a compression function. So it takes inputs of fixed length and also outputs. It's also fixed length, but it's just shorter. So far so good about the.
Yep. All clear so far.
Okay, that's good. And then we go to the next section. Basically, we tell you this trick because of this, the fact how SHA-256 works. We can leverage this fact to do some cool things actually. So if you look at this graph, what you can find is because it is an iterative process, you go through a lot of iterations and doing the same thing, and you have an internal state. So what that means, you can actually cut from any chunk, right? For example, I can cut from chunk 2, and then I can use the internal, if I know the internal hash so far, the internal state, without knowing all the previous chunks. All the previous chunks pretty much compressed to the current state, right? Which is the hash, right? So here, so this is everything before it is compressed to H2.
Yep.
So here, this H3, same thing. When you go to
so
this is
similar to ASIC boost, isn't it? The technique we use in mining.
I think I briefly studied, but I don't quite remember. How's that related? I think you have an overt and covered.
Yeah, exactly. And there are some, I think because the nonce is in the second or in a later part of the chunks. I think 2 chunks basically, and the nonce is in the second part, so you don't have to do the first part again and again. I think something like that.
Oh, okay, good to know. Yeah. So are all the mining machines now use this technique, or is this like some patent or something?
No, I think most of them use it. Yeah.
Okay. All right. Yeah. Cool. Yeah. Good to know. It's also used somewhere else. Okay. Good to know. And so what this means, you can take the internal hash, the internal state, which is a representation of all the previous chunks, and then you don't need to know the previous chunks. You can get to know the partial hash, and then you know the remaining preimage. Then you can also derive the same hash. It's going to give you the same number without knowing all the previous chunks. So this is also how attackers can attack this kind of hashing algorithm, because if I give you some hash for a message without knowing the original message, it can be like a password, right? So for example, without knowing this, I can derive some new messages appended to the original message, because if I can know the SHA for message 1 is equivalent to know this, right? And then I can pair the message 2, I can append it to the original message, and then I can derive the new hash without knowing the original message 1 here. So
would that work if you have a padding on the original message?
Oh yeah, you have to also know the padding, of course.
Yeah. Okay. Yeah.
Because, for example, this it doesn't work all the time, but a lot of time the attacker can somehow get to know if you know how, okay, let's talk about a little bit about the padding. So padding, actually, you need to know the length of the message, then you know the padding.
Yeah, okay, yeah.
You have 1 and you have zeros, and then you have the length of the message. So if somehow, for example, the password, for example, the message is the password, right? It can be, you can try different lengths, because I don't know about you, but when I type my password, is not like 1,000 bytes, right?
Yeah.
You can even just enumerate all the lengths and then try. So it's not easy. So a lot of times you can figure out the padding. Yeah, good point. And then you can append it to any message. So you can sometimes you can attack in this way. So instead of using this as an attacking technique, so we actually flip this on the head and use it for good, hopefully. So how do we do that? For example, a lot of times, as we mentioned, we use SHA-256 to, get some digest for some message. For example, transaction ID, right? So transaction ID, you basically take the raw full transaction and then you hash it using SHA-256 twice, right?
Yep.
And then there's some problem for us because it's not a attacker surface, but sometimes you probably heard about the up push transaction technique, right? So for most people who use, if not all the people who use sCrypt, we have this up push TX. And a lot of times, from the preimage, transaction preimage, sCrypt preimage, you can know the transaction ID. That's all in the input, right? So, but what if you want to know all the previous, your parent transaction? Because you know the parent transaction ID, usually you can push the full transaction and then hash it twice and make sure it matches the transaction ID, right? That's how you usually get to know your parent transaction. But that can sometimes be problematic, right? For example, what if the previous transaction is huge? You have very complex, let's say, script and also huge unlocking script. So in this sense, but what if you only want to know a certain portion of the transaction? You don't want to put the whole, usually what you do, you have to push the full transaction, right? Because if you know the transaction ID, which is the hash, and the only way you can match the full transaction is to have it fully injected, then hash it twice, right? And until today, right? Because with this technique, what you can do now is, instead of previously, because you know this hash, right? You have to push the whole, for example, the transaction ID for the parent transaction. You have to push the full parent transaction. Doesn't matter how big it is. But with this technique, you can only push, you only need to push like the trailing part, the last part of the full transaction. And then you can use the partial hash to combine with this two. You can derive the hash for the transaction. Does this make
sense? Yeah.
So depending on what you need, if you want to know the full transaction, you can do that. But what if some certain cases, for example, in this case, in our example, I just give you a toy example. You only want to know the log time of the transaction. And if we go to, a transaction format for the Bitcoin transaction, we know the last 4 bytes is actually, if this is the Bitcoin transaction format diagram, basically what if I only want to know the log time, right? For example, I want to make sure, this log time is, every time I spend it, I have to increment the log time. For example, you want to do some kind of like almost like let's say inheritance, or you want to do like a Bitcoin faucet, right? Because if you want to control it with a smart contract, every time somebody redeem it, you want to postpone. Let's say they can only redeem it once in a day, right? So you can also use this trick. But anyway, this is just a toy example. You want to know the log time. Before that, without this technique, you have to push the whole thing, right? Which is not always good, especially with, you know, the inputs output, they can be huge. Also for the script size, it can also be huge. So you don't want to push the whole thing. You can only push the last 4 bytes, right? So, you know, you can get the partial one, which is only contains the last chunk that contains the log time. So you can, you know, use this partial SHA-256 algorithm we just derived here, and you can hash it, and then make sure it matches the transaction ID. In this sense, you are sure this is the partial transaction. You are not a spoof. So then you can read the last 4 bytes, and you can get the end log time for the parent. But this is a very simple example. Just demonstrate how you can use this partial hash and the remaining chunks to derive the final hash. So here, just give you a sense. You know, this is pretty much, if you anybody who happen to know the internal of how SHA-256, this is all the magic number we talk about, and also this is for each chunk, you have to go through this kind of like a mechanical process. So it's pretty long. So you can see this but it's all like a shuffling and then shifting and then truncating some bits and words. So this is how it works internally. Hope this can help. I think this can help. Probably not when your transaction is very small. The premium is small, is probably not going to help, because you are adding a lot of you know, SHA-256. You are implement this in sCrypt or sCrypt, so it's going to add a lot of overhead. So this only makes sense when your original transaction is very big. So maybe I think that this is in the kilobytes range each iteration. So when your transaction is, let's say 10 kilobytes or 100 or 1 megabytes or even bigger. So this can save you a lot of bytes by implementing SHA-256 in the code itself. So any questions so far, Liam, here?
No.
Okay,
no,
cool.
It's interesting.
Yeah, so this is a very good trick. And just to say, it does not only apply to SHA-256, it applies to all the algorithm that use this kind of like a chaining and looping construct and also maintain internal state to compute the hash. So that, fortunately, or you can say that unfortunately, because it suffers from this attack, the length extension, but all the most used SHA-1, SHA-256, and also RIPE-MD 160 is all basically all the hashing algorithm that's typically used in Bitcoin. They can use this technique. So that means wherever you have a big preimage, you don't have to push the whole preimage to verify it hashes to a certain value. For example, transaction ID or Bitcoin address, you can only push the last parts which you care about, and then combine it with the internal hash. Then you can check if the final hash matches. So I'm going to stop here. Any questions or comments or anything else you want to talk about?
No. I mean, it's interesting. I'm trying to think of how we could use that. I mean, there must be very many smart ways you can use this, not just to save size of transactions.
Yeah,
also
definitely.
to speed things up, like the ASIC boost does.
Yeah, so I would, for me, because our blog is dedicated to smart contracts, so that's why I only focus on smart contract side of things. But as you said, right, even for outside of a script, you can probably, one thing you mentioned about, I think I have to check again, the ASIC boost. You said it's something similar here.
Yeah.
You can kind of like keep the internal state, intermediate state. You don't have to redo everything.
Exactly. Yeah. And when you're mining, you're looking for, you know, so many hashes per second, so many millions and millions of hashes per second. It makes a lot of difference if you don't have to hash the whole thing.
Makes sense. Okay. And what other potential way you can think about? For me, I don't know. Just randomly think. Could this somehow speed up like SPV or something? Because SPV, right? You can also do a lot of hashing there for the Merkle proof.
I was thinking of recognizing different sorts of transactions somehow. That we do a lot on what's on chain.
Okay,
So
basically, go ahead.
No, I was just thinking, I mean, if we hash a script, we have variable parts of a script, don't we? But there's often parts of a script which are non-variable. So I'm just trying to think if there's a way we can use this as well to.
I see what you mean. Okay. So a lot of time, because if someone's using script in the apps, and they have to pretty much filter all the other transactions. Somehow you have to get to know this. Oh, very interesting. Yeah, I think I don't know if you heard about Connor Murray. Basically, he recently published something very closely related. Basically, he's trying.
No. So I was speaking to him earlier on actually. So maybe.
Oh, really? Okay. Yeah. Now you remind me. Maybe something you can plug in here, so you don't have to. Because if it's somehow the transaction, the script part is very long, and then you hash it. I think it's probably not a problem for now, but if you go in the future, maybe you have terabyte blocks, right? So you're hashing, and most of them, I would say, is maybe have some pattern, like what you just said, right? So you have script part, you have a constant part, which is kind of like a template, and then you have the variable part. So maybe you can somehow, if the constant part is like what we do stateful contract, right? So the code part is always fixed. So you may be able to compress it with this hash, because this doesn't change, right? So and this is only the variable part, and then you can hash the whole thing by just you don't have to hash the whole thing, because the most part it doesn't change, right? So you can always use the same. Okay, cool. Haven't thought about that. Okay, it could be a good optimization trick. Okay, nice. Another potential, I think that's one, definitely filtering script patterns. That's definitely for sure. And of course, you talk about the hashing, the mining itself. So
that's
SPV. I don't know if you. So currently, does what's on chain offer SPV proof?
The Merkle proof.
The Merkle proofs, yes.
Yes, we do.
Oh, okay. Yeah, I don't know. Just thinking out loud. Maybe when you do all them, somehow they have a fixed part to serve. I don't know if that's possible. So you can it's like a caching. You can cache this part because it doesn't change. So basically this means if you have a big chunk of preimage data you want to hash, and you already know that if some part you don't care, or it's always fixed, so you don't have to redo the work again, right? This hash pretty much is the SHA-2 fixes for all the previous chunks, right? So you can somehow, I don't know, cache it, and then you don't have to redo. Cool. Yeah, it's good to think a lot about. For me, I think for our articles, as I said, mostly focus on the smart contract side of things. So filtering, hashing.
No, it's good to. It's a good blog post. I shall read it.
Yeah, and we not only so we have a huge list. So if you have not followed it yet, I strongly recommend you go there. So the easiest way would be just everything is from sCrypt.io. So you can go to the bottom. You can click the Meetup link. That's the official blog.
Okay. Yeah.
So we publish, I think, if not always, but mostly weekly, probably 1 or 2 techniques. So it's actually pretty popular. You can also subscribe by email. So anytime I publish something new, you can get an email from it.
I shall do that.
Yeah, definitely try. And
next week I'll come back with some more questions.
Yeah, definitely.
But maybe on some older blog posts. I don't know.
Yeah, I think usually we go through this is like a standard agenda. If nobody else try to have, we also bring projects that use sCrypt or not. But there's vision, we want to know what is the problem they are working on. For example, we had Stefan a few days ago. He's using that as a time stamping service. We also have Connor. He also talk about the filtering technique. So if you have anything, you want to, either it's a tile or you may have a side project. Definitely, you want more people to know about it. Definitely come here and we try to focus on the tech side of things. So I know we have a lot of talks and shows in BSV, but I think we are one of the few that's like a technically focused.
Yeah. Okay.
And it's happening every Friday. So anytime you want to come.
A good time for us as well in the UK.
Oh yeah. You're not taking a Friday evening off or something, or?
Well, I shall begin that after this.
Okay.
Yeah, it was.
All right.
It was very interesting. Thank you.
Okay, thank you for coming. Any other comments or thoughts or what's update you want to the developers want to know coming from Watson Chain or Tao side? Any hints?
No, I shall. I'll come back next week and give you an update on that.
Okay.
So there'll be more things happening next week, I think.
Oh, okay. Look forward to it. Seems some big things coming soon. So.
Yep.
Stay tuned.
Okay.
Okay. Thank you.
Thanks for that. Thanks.
Have a great weekend. Okay.
You too. Cheers.